Hello. So I'm going to present this paper, Hand Avatar, Pre-Pose Hand Animation and Rendering from Monocular Video. So the contributions of this paper are as follows. This paper proposes a hand avatar framework, which is the first method for neural hand rendering with self-occluded illumination. And then they developed a nano HD and a local pair occupancy field that fit hand geometry with personalized shape details, and they proposed a self-occlusion aware shading field that can render hand texture with faithful shadow patterns. And their proposed framework is end-to-end developed for free pose realistic hand avatars. So, well, as the name itself suggests, it can work just on a monocular video. We do not need multi-view frames for this to work. Let's get into it. So for those who are not familiar with the mesh setup, so in this scenario, mesh, we represent the hand using a mesh structure, which is basically just, as you can see, it's represented by some set of triangles, and each of the triangle is usually referred to as the face, and the corners are referred to as the vertices. And this Mano model deforms these hand meshes, and this deformation is controlled by this parameter beta. And the pose of the mesh is denoted with this parameter theta, with the dimension b times 3. And this b is equals to 16 in this setup. And the 16 comes from, as you can see in this image, it just refers to 16 different part bones, or like 16 different sets of bones. So for every bone, we have a 3D representation in the pose parameter. So one of the thing they do in this proposed framework is they increase the resolution of this Mano mesh. To lift the mesh resolution, they uniformly subdivide Mano template mesh by adding new vertices on the edge middle points, and then skinning weights of added vertices are given with the average of their seminal vertices. So during training, we do need a mesh of the hand to sort of capture the geometry of the hand. Before I go further, let's review what linear blend skinning is very briefly. So let's assume you have a mesh that looks like this, represented by two different vertices, let's say. And when we are going to deform this mesh, change the pose, each of these vertices has a weight associated to it that represents to what extent they influence the deformation in the surrounding regions. So let's say in regions like these midpoint, when we sort of take this, we want to deform it in this shape, in this region, like this is affected by both this part and this part. So let's say in a scenario where both the vertices have a weight of half and half at this point. So the specific region here would be deformed to an equal extent by both the vertices. So after the deformation, this yellow point here would just remain in the middle between this red and the blue. So this is what, like, this is basically a brief high-level intuition of what linear blend skinning is. So this upsampled Mano mesh, they refer to this as Mano HD. And since Mano itself, like I said, is the deformation is represented with the parameter beta, Mano HD will also have this parameter beta. But the issue with this is that So the downstream task of this paper is sort of like, let's say there is a video of hand from a single viewpoint doing different poses. So the downstream task is sort of to create a 3D representation of the hand as realistic as possible, of those same poses being made in the input image. So as there's motion within the video, of course, the mesh that was defined at the beginning would have to be changed to fit those different poses. And since to deform meshes, we need this beta parameter, which won't be available during test time, they introduce a neural net component and MLP to replace this beta parameter, this M shape. So what happens here is first they start with some template vertices, then this MLP component controls to what extent this template vertice is going to be deformed to fit the pose represented in the input video. Yeah, this M shape takes as an input these quantities, where these are basically the template vertices and the positional encoding of the template vertices, and just concatenating it for all the frames in the video. And the MLP can be trained with monocular video data and IOU loss. So the loss is represented like this, where the quantities are basically silhouette rendering, linear blend skinning, and ground truth silhouette. Basically, this silhouette, you can sort of think of this as this mask that is denoted here. So this is what's used to supervise this mesh deformation to ensure that it matches the pose represented in the input video. So yeah, so far, yeah, first you like upsample the nano HD, and then you perform shape fitting and then skinning, and then let's move on to the next parts. So next component that I'll be discussing is the local pair occupancy field. So the purpose of local pair occupancy field is that, let's say we define a 3D space, and we want to query specific points in this 3D space. So for a query point Q, this pair of component predicts the occupancy value to describe whether this query point is located in or out of the surface of the mesh. So when the Q is perfectly like right on the faces of the meshes, the occupancy value is going to be 0.5. And when it is outside the mesh, it's going to be less than 0.5. And when it is inside the mesh, it's going to be more than above 0.5. So I'm now going to discuss how we can get these values. So pair of component takes input from this fitted mesh that I discussed before. And then it also takes inputs from the ray that has been casted, and it samples a query point from the 3D space along the ray that has been cast, which is this Q here. And from the mesh, within the mesh, it divides the mesh into 16 different part bones that we have. From each of the part bones, it samples some fixed number of points from the surface, and it forms a sort of 3D cloud representation like this, as you can see here. And it takes the or 3D cloud points and the normals, and then it transforms them into a part space canonical space. So this part space canonical space is basically just a coordinate system shared by each of the 16 bone parts. So once we have transformed each of these 3D cloud points and the normals, we feed it as an input to PointNet, which is denoted as this Q part here. And if you're interested in the architecture of PointNet, it's yeah, right here. It's rather a very simplistic architecture. So once you have the output of the so output from this PointNet, you sort of pair them up with the query point to form the sort of geometry embedding for each of the 16 bone parts. And then these, so for each of the 16 bone parts, you have the output of the PointNet concatenated with the query point. And then you feed each of these, and then comes the next part, which is the local pair decoder, which I'm going to discuss next. To explore interpart relations, previous works usually fuse per bone features according to the kinematic tree to form structured representations. So kinematic tree is basically a sort of a hierarchical map of sort of rigid bodies that are not connected to each other. So this is like a map where they're arranged according to their location, but in kinematic tree representation, it's assumed that they're not connected to each other. So previous works usually represent hand in this manner, but in this work, the authors argue that like hand is basically, yeah, we all know like that's not the case for hands. Each of the bones in our hand are definitely connected to other bones in the hand. So instead, they assume that there are physical connections within the bones. And the next part, this local pair decoder sort of captures the relationship of each of the bones and their connections as well. So yeah, as the writers themselves narrate, the intuition is that the local part shape is not related to the kinematic tree. Instead, there's a strong relationship between parts. Hence, we define local pair as two parts that are physically connected. Then this, what this Q pair, which is also based on PointNet, what this does is it takes input of these part bone geometry embeddings, like pairs of part bone geometry embeddings like this. So there's, let's say we are trying to find the relationship of one particular bone, and then this DB hat would be bones that are connected to this bone B. And so you iterate over all the connected bones, and then for these pair of bones, you get an output out of the PointNet, and then you take the maximum for whichever pair you get the maximum value, you take that and you feed it to this sigmoid function, and then you have this pair of value. Then you get the occupancy value for that bone for the given query. And then you calculate the global occupancy value for the query point by fusing the part level feature for each of the 16 part bones. So you basically just take the occupancy value for whichever bone it had the highest value. That's it. So basically the intuition, the motivation behind this was that though through the pair partwise decoder, part boundaries sort of become blurred. So basically, this is just taking into consideration for each of the bones, capturing geometry beyond the individual bones and to include their connections as well. And then this local pair occupancy field is pre-trained. And the way they do this is in the point clouds, like they sample some specific number of points, represented like n number of points, which is taken as the training data, and they just calculate the MSE loss for the occupancy values. So far we have, so to summarize the purpose of this pair of component, you get the query from the 3D representation from the array that has been cast into this 3D space, and you get the cloud points and the normals from the mesh, and then you get the individual occupancy values for each of the individual bones, and then you finally get the global occupancy value. And that's how you, like, this whole architecture sort of captures the geometry of the hand as represented here. So next part would be volumetric rendering. So as you can, like, as you see in this illustration, the occupancy values that have been extracted are sort of being fed into the outputs of the self-occlusion hour shading field during volumetric rendering. And what happens in self-occlusion aware shading field is that it outputs the illumination. It outputs the illumination and the albedo map, and then these two are combined to get the sort of the avatar or the final output. So volumetric rendering, just what it does is it just, for each of the 3D points, it gets the albedo map and the illumination map, and it just creates this whole structure. So the volumetric rendering equation is similar to how it is in NERF, except the colors and volume densities are replaced by either the albedo or the illumination or this AU, the combined sort of shaded albedo map. And for each of, whenever we try to render each of these three quantities, every time we need the pair of, so the occupancy values as well. So next, let's look into how albedo field is generated. So what is albedo? So like you see, the albedo is basically the intrinsic color and the illumination would be the information how much light is reaching each of the in different regions on the hand. So when you multiply the two, you get this shaded albedo map, which has, as you can see, like in regions where light hasn't reached, it's shaded out because of this illumination values. And now let's look into how albedo map is generated. So first, again, takes some sample cloud points. Some cloud points are sampled, and n different points are taken from this 3D point. And for each of those, we get the albedo encoding here, represented by this AP, and positional encoding to be used for the illumination MLP. And then once we get these, and another thing is that in this 3D cloud that has been sampled for this self component, they use the barycentric coordinate system. What this means is that the purpose of this coordinate system is that, let's say, of course, for different frames, the pose of this mesh is going to be different. And barycentric coordinate system is basically coordinate system sort of with respect to the triangles on the surface of the mesh. So as a result of this barycentric coordinate system, no matter whatever the pose is of the hand mesh, we get to identify specific regions of the hand, basically. That's it. So again, we have the query samples we sample the queries from the ray cast into it, and 3D cloud points from the mesh. And we get the albedo map, albedo encoding, which is fed into the MLP, and we get the albedo value for this particular query point. And we perform volumetric rendering, and while doing it, we need the occupancy value for that query point, which we get out of the output of the pair of component. And then, we have our albedo map. But for the illumination map, as you can see, besides just the encoding for the positional encoding for the cloud points, we also have another input coming in here from pair off. And next, I'll get into that. That is basically the directed soft occupancy field. So going back, in this region, for local pair decoder, we were using the sigmoid function. For directed soft occupancy, that is replaced by instead this modified sigmoid function of sorts, which has this extra parameter tau. The reason for doing this is that the authors argue that the output of the pair of component tends to be, in most cases, almost binary. So to sort of soften this behavior, they add this tau parameter in their function. And so the purpose of this directed soft occupancy is basically to find the impact of self-occlusion on illumination in different regions on the hand. So this soft occupancy is defined as, let's say, for a ray that has been cast, ray R, that can reach a point Q in the 3D space, the directed soft occupancy represented like this for a particular bone, for a particular Q, for a given ray is defined as the maximal value on R before the ray hits Q. So before, what we were doing with the occupancy value was that, let's say, this is a forefinger, for this given forefinger represented by these 4 bones. Let's say we are querying this point Q, which is sort of out of the mesh. And in case of when calculating the occupancy value for that Q, we would have values that would be associated to basically around that region. But for this directed soft occupancy, what's going to happen is it takes the occupancy value not at that specific region Q, but whichever point returns the maximum occupancy value for the ray from which Q was sampled. So basically, for the given ray, we sample points before Q, and from the origin of the ray up to the point Q, whichever point returns the maximum occupancy value, that is going to be the soft occupancy value. So basically it would be something like this. So soft occupancy is, of course, more than 0.5 when the point is inside the mesh. So for this bone B3, part bone B3, represented in purple color, after we perform directed soft occupancy, because so regions along the ray, which is near or sort of inside the region of B3, would of course have the maximum value, and that would be the one chosen for directed soft occupancy. So this is sort of meant to represent the fact that because there is another bone part before the region Q, light is not going to reach that point Q. So that part is going to be shady. That's the overall intuition for this component. So yeah, that's the input that comes into this MLP when we try to calculate the illumination. So that is it. Now let's just look into the results. They couldn't find the exact architecture that's built for this kind of downstream task. So the architectures they compared against were self-reconstruction and human nerve. And they tested on the Interhance 2.6M data set, which has frames like monocular videos, as well as the mesh for each of those frames. And yeah, these are the results, and they are pretty much best in every single metric. And these are this is what the qualitative result look like. This is the ground truth, and like as you can, they even show some failure cases where they represent the regions better than the self-reconstruction and human nerve. And as you can see, like regions where sort of light fails to reach, human nerve and self-recon sort of like fails to apply the shading, but Hand Avatar does quite a good job of it because of their illumination map to apply this shading. So that's it from me. Thanks for listening.